Right, consider a loop, a circuit like this. It has some switch S, okay, and there's a battery here, and there's a resistor here, okay. Let's say EMF of the battery is epsilon, R is the resistance. The current on this loop is, let's say, I. Now the question we should ask in order to understand self-induction and self-induced EMF is, what is the current in this circuit? Now using Ohm's law, this should be your answer. But here this answer is only valid for larger times. I'm going to write that larger times as t tending to infinity. Okay, so only then it is true. What it means that it takes some time for this I to build up to this value. It does not get to that value instantaneously. Okay, and why does that happen? Well, let's say initially there's no current in the circuit, okay, and then I push this switch down so that the circuit is completed. That means that the current I begins to grow in this circuit. Now as it is beginning to grow, first of all, if there's current I in the circuit at any moment at the time, there's also magnetic field, and using right-hand law, the magnetic field are concentric circles all along the circuit. Now that means that the magnetic field, and remember my distinctions of induced magnetic field and induced current and current, okay, just remember always. So the magnetic field is coming out of the page like this. So out of the page is this, okay, and because of that the flux is also increasing out of the page, and if flux is increasing out of the page, the induced magnetic flux will be in the opposite direction. That means the magnetic field induced will be in the opposite direction, that is into the page, so that it counteracts that change in flux. And because of that induced magnetic flux or induced magnetic field, there will be an induced current, which I'm going to call as I induced, I sub IN. So the point is, because of this current that was trying to increase from zero, there is a flux that is also trying to increase, going upwards out of the page, out of the plane of the circuit. That's why there is a induced magnetic field into the page, or towards the direction opposite to the direction of the magnetic flux. So because of that, there is an induced current in the opposite direction of the current. Now what we call this is like the reasoning that we give for this induced current is, we say that, okay, you can imagine that there is like a tiny little battery over there whose voltage is some epsilon L, okay, but its polarity will be opposite of the EMF epsilon. So because of that, the current is going in the different directions. When I said opposite, I should really be making it like this. So because of that, the E induced is in the opposite direction of current I, okay. So there's an induced EMF in there, and because of that, there will be a tussle between the current that is there because of the EMF epsilon and the induced current that is there because of the EMF epsilon L, and that is why it takes some time for the current to reach to this value, that is epsilon over R. Now we will see mathematically how this comes out to be, but qualitatively this is what happens. Now this effect of having this EMF EL, which is also called back EMF, is called self-induction. Self-induction because, you see, the induced magnetic field and induced magnetic flux and induced current, they are all because of the current of the loop itself, and that is why it's called self-induction. And the EMF epsilon L is called self-induced EMF.